Okay, as we mentioned before, operation research deals with two approaches: deterministic approach and stochastic approach. Let's just look to these two approaches. Through the conditions and circumstances under which decision makers take an optimal decision. Usually, decision maker takes decision under four circumstances or four environments: under certainty, under uncertainty, and risk, and conflict. These three four environments under which, or four circumstances under which decision maker takes an optimal decision. Okay, so deterministic methods is based on full information. So data and information are given. That means decision maker takes an optimal decision under certainty. Here there is no risk. Information and data are given. So he can formulate a linear programming. Linear programming is very in-depth and very relevant and very closer to what? To decision under certainty. While stochastic methods usually used under circumstances of uncertainty or risk or conflict. So stochastic methods usually uses the approach of mathematical techniques, or actually the theory of probability. Theory of probability is most relevant to the stochastic methods. The deterministic methods only is a very good technique for the following operations research methods, like graphical method, simplex method, big N methods, two phases method, the problem of transportation, and assignment model, etc. So now we are going to focus on the deterministic methods, which include graphical method. So that's why we describe graphical methods as an application of linear programming. An application of linear programming. So a linear programming problem involving, in case of graphical methods, two decision variables. Two decision variables. And this, when there are two decision variables, we can use graphical methods. For models with three or more than variables, the graphical method is impractical. This method is easy to understand and useful to explain the basic concepts of linear programming. Okay. The redundant constraints are automatically eliminated from system. Multiple solutions, unbounded solution, and invisible solution are clearly defined using graphical methods. Sensitivity analysis can be represented by means of graphs also. Okay. So why we use graphical method? Because each axis of graph represents one decision variable. Product X on vertical axis, product Y or X2 and horizontal axis. So graphical method is applicable only to solve the problem with two decision variables. Okay. That's why the first step in the graphical methods is to plot the visible solution space that satisfies all the constraints simultaneously. Now, the given is, the givens are objective function, constraints, and negativity condition in order to apply the graphical method. These three components is known as the component of what? Of linear programming. Objective function, constraints, and non-negativity condition. So if these three components are satisfied, then we can use graphical methods to find an optimal solution for objective function with two decision variables. Okay. Steps of the graphical methods, or steps of application of graphical methods, or how to apply the graphical methods. 1. The problem is expressed in the form of a mathematical model. 2. Consider each inequality constraint as equation, or convert constraint into equation. Plot each equation on the graph, as each equation will geometrically represent a straight line. Shade the visible region and identify the visible solution. Every point on the line will satisfy the equation of line. If the inequality constraint corresponding to that line is less or equal, then the region below the line lying in the first quadrant, due to non-negativity of variables, is shaded. For the inequality constraints with more or equal sign, the region above the line in the first quadrant is shaded. Understand? The point lying in common region will satisfy the constraint simultaneously. Thus, the common region obtained is called visible region. This region is the region of visible solution. The corner points of this region are identified. So, in the next slides, we can apply practically these 4 steps. We can apply these 4 steps practically using various examples. Referring to the previous slides, let us add the last step 5, finding the optimal solution. The value of z at various corners points of the region of visible solution are calculated. The optimum, maximum or minimum z among these values is noted. Corresponding solution is the optimal solution. Let's see. Solve the following LPP, linear programming problem. LPP stands for linear programming problem graphically. What is given here? X maximum or max z equal 3x1 plus 5x2. That's me. Firstly, this linear programming problem about what? About profit maximization. Once it indicates max z. There are 2 decision variables, x1 and x2. 3 is the profit of 1 unit of x1 while 5 is the profit of 1 unit of X2. Now, subject to the following constraints: x1 plus 2x2 less or equal 2000, x1 plus x2 less or equal 1500, x2 less or equal 600. These three constraints means that these two products, x1 and x2, pass three phases of production or three machines or whatever, three processes respectively. And actually x1 is a non-negativity condition, x1 and x2 more or equal 0, obviously. So let's step by step view how we can apply graphical method solution. First, to represent the constraint graphically, in inequalities are written as equalities. Every equation is represented by a straight line. 2. To draw the lines, 2 points on each of the lines are found as indicated in the following table. Intercept. Now, step 1. Convert the constraints into what? Into equations. First step, to convert the constraints into equation. What that means? That means constraint 1 will equal x1 plus 2x2 equal 2000, and x1 plus x2 equal 1100, and x2 equal 600. Three constraints. So using geometrical methods to find the value of x1 when x2 equals 0, and to find x2 when x1 equal 0. Let's see how we can do this. Okay, check this table. This table contains 4 columns and 3 rows. Equation: x2 intercept when x equals 0, x1 intercept when x2 equals 0, and this is a point x1 x1 and x2 on the line. Okay, now check the first equation. x1 plus 2x2 equal 2000. If x1 equals 0, then the remain is 2x2 equal 2000. x2 equal 2000 over 2, 1000. If x2 equal 0, then x1 equal 2000. So the points 0, 1000 and 2000, 0. So the common is 2000, 1000. Now let's go to the next equation. x1 plus x2 equal 1500. Of course, x1 equal 0, x2 equal 1500, x2 equal 0, x1 equal 1500. Okay. x2 obviously equal 600 and x1 equal 0. x1 axis, x2 equals 0, x2 axis. So plot each equation on the graph. Now we are facing three equations where the first point, three equations corresponding three constraints. Now we are going to plot these three equations on the graph. Let's see how we can do this. Firstly, x2 equals 600 when x1 equal 0. This is the last. So the common points for the first constraint 2000, 1000, and the common point for the second constraint is the 1500 and 1500. D'accord? So now after plotting the various equation on graph, we found these the border point A, B, C, D. A is given as 1000. A represents x1. A equal 1000, 2000 when x1 when x2 equals 0. So 2000, 0. And check D. D, it is 0, 600. The last constraint, the third constraint. Problem concern with 2 points C and B. Sorry, B and C. B and C are the point of intersection of lines or equation x1 plus 2x2 equal 2000 and x1 plus x2 equal 1500. So we need to solve this in this simultaneously. The intersection point between C and B, we need to solve this equation simultaneously in order to find the values of x1 and x2. Let's check the following table to show how we calculated. So now check the three corner points. A, x equal 1500, x2 equals 0. The intersection points B, B, x1 equal 1000, x2 equal 500. The next intersection point C, where x1 equal 800 and x2 equal 600. The last intersection point is x equal 0, x2 equal 600. Now we are going to substitute these values into z or graphical or objective function. Objective function state z equal 3x1 plus 5x2. When the corner point is A, where x1 equal 1500 and x2 equal 0, then z equals 3 times 1500 plus 5 times 0. So the result is 5500. Let's move to the next corner point B, where x1 equal 1000 and x2 equal 500. Okay, so z equal in this case 3 times 1000 plus 5 times 500, and we got 5500. Let's move to the next corner point where C, where x1 equal 800 and x2 equal 600. Let's substitute this value and we will get z equal 3 times 800 plus 5 times 600. The result is 5400. The last corner point where D, where x1 equal 0 and x2 equals 600. So it will be z equal 5 times 600 equal 3000. So once we are looking for profit maximization, then the best choice is to produce 1000 units of x1 and 500 units of x2, because this combination gives 5500 profit. Therefore, the maximum value of z occurs at B 1500. Hence, the optimal solution is to produce x1 equal 1000 units and x2 equal 500 units. Example 2. A and B are two products to be manufactured. Unit profits are $40 and $35 respectively. Maximum materials available are 60 kg and 96 hours. Each unit of A needs 2 kg of materials and 3 man hours, whereas each unit of B needs 4 kg of materials and 3 man hours. Find optimal level of A and B to be manufactured. So this linear programming problem faces two decision variables. Let x1 and x2 be the number of product A and B to be produced by the manufacturer respectively. Therefore, the total profit has to be maximized. And then the objective function is max z equal 40x1 plus 35x2. So, as mentioned, $40 is the profit of 1 unit of x1 and $35 is the profit of 1 unit of x2. The first step is to formulate objective function according to the information and data given or stated by the example. Let's see how we can formulate the constraints. Check the next slide. Continue. Constraints. The manufacturer has limited materials and labor time for manufacturing product A and B. There are 60 kgs available and 96 hours available for labor. Thus, total processing is restricted. Let's see the material constraints. 2x1 plus 3x2 less or equal 60. 2 is the cost of 1 unit of x1 and 3 is the cost of 1 unit of x2. The total cost must not precede 60 material, 60 units of material. The next constraint says that for x1 plus 3x2 less or equal 96 is time. So the total production of x1 and x2 must not precede 96 hours. Finally, the complete linear programming problem is max z equal 40x1 plus 35x2 subject to what? The constraint 2x1 plus 3x2 less or equal 60, 4x1 plus 3x2 less or equal 96, and obviously the non-negativity constraint is x1 comma x2 more or equal 0. Let's move to the next stage. Okay, to represent the constraint graphically, the inequalities are written as equalities or equation. Every equation is represented by a straight line. To draw the lines, 2 points on each of the lines are found as indicated in the following table. Intercept. Now, there are two equations represented two constraints. The first equation is 2x1 plus 3x2 equal 60. So assume that x1 equals 0, then 3x2 equals 60, x2 equals 60 over 3 equal 20. And if x2 equals 0, then 2x1 equal 60 and x1 respectively equal 30. The point of x1 and x2 are 0, 20 and 30, 0. That's correct. Let's move to the next equation where 4x1 plus 3x2 equal 96. If x1 equal 0, then x2 equals 32. If x2 equals 0, then x1 equal 24. Point of x1 and x2 are 0, 32 and 24, 0. x1 equals 0, x1 equals 0, x1 axis, x2 equals 0, x2 axis. Plot each equation on the graph. Put into account. This is a result of plotting the corner points. This is a visible region. So A, B, C and 0, D. So this is a border. A is a border of visible region. A 20, 0, 20, x2 the vertical axis and x1 on the horizontal axis. So now you have to focus on these 4 points. The null point, okay, origin point 0, 0, and you can forget it. A 0, 20. B is intersection point between two equations. We need to solve them simultaneously to find x1 and to find x2. C is given when x2 equals 0, x1 equal to 24. That's okay. So let's transfer this information to the table. Let's transfer this information to the table. It will be very clear. So we converted the previous corner point into this table. There are 3 corner points: A where x1 equals 0, x2 equal 20. We got the points of the values of the points of the point B, 18 and 80, and the last values of point C, 24 and 0. Let's substitute these values to Z. Z equal is given, of course. Z equal 40x1 plus 35x2. So when A is 0 and 20, so Z equal 40 times 0 plus 35 times 20, and Z equal 700. The next corner point B, Z equal 40 times 18 plus 35 times 8. The given is 1000. The last corner point is 24 0. Z equal 40 times 24 plus 35 times 0, and the harvest is 960. Therefore, the maximum value of Z occurs at B equal 18 and 8. Hence, the optimal solution is to produce X1 equal 18 and X2 equal 8. This is an optimal because this combination of X1 and X2 yields very high profit comparatively with other points. The application of graphical methods. Assume that max Z equal 40x1 plus 50x2. That means we are talking about the problem of maximization. This objective function indicates that we are talking about problem of maximization. Given also two constraints subject to 3x1 plus x2 less or equal 15, this constraint number 1, and x1 plus 2x2 less than 12, constraint number 2. The non-negativity condition x1, x2 more or equal 0. Solution. The first step is to convert constraints to equations. Let's see. To convert the first constraint to equations, it will be 3x1 plus x2 equal 15. Assume that x1 equal 0, then x2 equal 15. If x2 equal 0, then x1 equal 15 over 3 equal 5. The coordinates x1 equal 5 and x2 equal 15. Let's move to the second constraint, where x1 plus 2x2 equal 12. Again, assume that x1 equals 0, then x2 equal 12 over 2 equals 6. If x2 equals 0, then x1 equal 12. The point is x1 equal 12 and x2 equal 6. Let's move to plot the graph. Based on our calculation and the coordinates which we found out, I would like you to center your attention on the 4 intersection points. The first is intersection point stand for original point, which is always 0 0 0 for x1 and 0 for x2. Point B denotes x1 equal 5 and x2 equal 0. Point C is unknown. We will find it by solving two intersection equation simultaneously. The last point is point D, where x2 equal 6 and x1 equal 0. هننقل الإحداثيات التي حصلنا عليها ونعبر عنها بيانيا. نقطة A تعبر عن نقطة الأصل، وهي نقطة تقاطع المحور x1 مع المحور x2. ثم النقطة B تمثل x1 بتساوي 5 في حالة x2 بتساوي 0. النقطة C غير معروفة، يجب أن نجدها من خلال حل المعادلة التي تعبر عن المنحنى، عن حل المعادلتين التي تعبر عن المنحنيين، نحلهم حل آني بحيث نحصل على إحداثيات النقطة C. النقطة دي هي عبارة عن x2 تساوي 6 عندما xc بيساوي 0. طيب، هذه النقاط التي حصلنا عليها يجب أن نعوضها في دالة الهدف. دالة الهدف اللي هي z equal 40x1 plus 50x2. إذن نحن هنا قمنا بالخطوات الأساسية لحل مشكلة البرمجة الخطية على أساس الجرافيكال ميثود، وهي مشكلة تعظيم. We mentioned before that the graphical method aims to solve the problem which consists two decision variables. Why? Because each axis represents one decision variable or one product. For example, looking to this graph, x1 represents vertical graph, or vertical graph represents the product of x1, and the horizontal graph expresses the product of x2. Now we are going, the second step is to plot these coordinates, which we found out by assuming x1 equals 0 to find x2, and assuming x2 equals 0 to find x1 in two equations. تم الرسم أو التعبير بيانيا عن الإحداثيات للمعادلتين التي تعبر عن الغيدين. We mentioned before that this problem consists of two constraints. Once so we have two equations or two curves. These two curves reflects the two constraints. طيب، قمنا بنقل الإحداثيات التي حصلنا عليها للتعبير عنها بيانيا. الإحداثيات التي تعبر عن نقطة الأصل هي A 0 0، ثم النقطة B وهي عبارة عن 5 for x1 and 0 for x2 ثم 12 x1 where x2 equals 6, 5 x1 where x2 equal 15. طيب. The law states that the zone of possible solution placed between the intersection point which close to original point. We determine the zone of possible solution as the closest points to original points. نقاط التقاطع الأقرب لنقطة الأصل، ولذلك قمنا باختيار النقطة B والنقطة C والنقطة D. لم نختار النقطة التي تمثل البوينت 12 ولم نختار النقطة التي تمثل البوينت 15 because they are far from the original point، لأنهم بعيدات من نقطة الأصل. هذا في حالة التعظيم. نحدد منطقة الحلول الممكنة من خلال نقاط التقاطع الأقرب إلى نقطة الأصل. في حالة تنمية التكاليف هو العكس تماما، هنختار النقاط الأبعد من نقطة الأصل، وفي هذه الحالة النقطة C ثم النقطة التي تعبر عن الإحداث 12 والنقطة C التي تعبر عن الإحداث 15. طيب إذن now we have to deal with 4 points A, B, C, because these 3 points will satisfy the problem of linear programming, which focuses on profit maximization. Otherwise, in case of minimization, we will choose the point C, the point which represents 12 coordinate, and the point which represents the 15 coordinates. Okay. Step 1, I would like to remind you about the steps of graphical solution. First, to convert the constraints to equation. Second, to solve equations by assuming x1 equals 0 to find x2 and x2 equals 0 to find x1. Step 3, we are going to draw the graph. Once we have 2 constraints, then we are going to draw 2 curves, each for 1 constraint. Each curve represents 1 constraint. Okay. And we will center on the intersection points that closer to original point. Given the objective function z equal 40x1 plus 50x2, let's substitute the points of the coordinates of each point. If point A equal 0 0, where that means where x1 at point A x1 equals 0 and x2 equal 0. 40 multiplied by 0 plus 50 multiplied by 0. So we will get 0 profit. Let's move to point B, where is x1 equal 5 and x2 equal 0. x2 equal 0. So 40 times 5 equal 200 and 50 times 0 equals 0. Then our profit is $200. So at the point C, x1 equals 3.6 and x2 equal 4.2. Let's substitute by multiplying 40 by 3.6 plus 50 by 4.2, and we will get $354. The last point is point D, where x1 equals 0 and x2 equal 6. Let's substitute 40 times 0 plus 50 times 6, we will get $300. طيب. سوف نقوم بتعويض إحداثيات كل نقطة من هذه النقاط. عند النقطة A x1 بيساوي صفر و x2 بيساوي صفر. إذا x1 بيساوي صفر معناها 40 في صفر زائد 50 في صفر، معناها حصلنا على Z، أي الربح بيساوي صفر. نمشي للنقطة B، عندها x1 بيساوي 5 و x2 بيساوي 0، معناها 40 multiplied by 5 equal 200 and 0 multiplied by 50 equal 0. So our profit is 200. لما نمشي للنقطة C هنعوض بدل x1 3.6 وبدل x2 4.2، اللي هتكون 40 times 3.6 plus 50 times 4.2، وهنحصل على ربح مقداره $354. النقطة الأخيرة the last point where x1 بيساوي 0 و x2 يساوي 6. x1 بيساوي 0 معناها فينيش، هنعمل شنو 50 times 6 اللي هي $300. So the highest profit equal $355. So the optimal solution is to produce 3.6 of x1 and 4.2 of x2 to get the maximum profit, which equals to 354. So what is the optimal solution? The optimal solution, that solution which gives maximum profit. الحل الأمثل هو الحل الذي يعطي أعلى مستوى للربح، وهو عندما ننتج 3.6 من السلعة x1 و4.2 من السلعة x2. The optimal solution, that solution which gives maximum profit. We will get maximum profit when we will produce 3.6 of x1 and 4.2 of x2. If the case is minimization, we will choose point B. Point A indicates that there is no production. Nonsense. The lowest cost in case of minimization is 200. Is 200. The graphical method faces various exceptional cases. Simply, these cases cannot be solved normally. Now, first exceptional case is multiple optimal solution. There is more than one optimal solution. Of course, this is the exceptional case. It's abnormal case. Now let's see one example of multiple optimal solution. When the linear programming problem faces more than one solution. Solve the following LPV by graphical methods, where MZ maximum Z equal 100x1 plus 40x2. This objective function subject to 5x1 plus 2x2 less than 1000, 3x1 plus 2x2 less than 900, x1 plus 2x1 less than 500, and x2 comma x1 comma x2 more than 0. First, we are going to represent constraints graphically. The equalities are written as equation. Actually, this in translation to convert constraint into equation. Every equation is represented by a straight line. To draw the lines, 2 points of each of the lines are found as indicated in the following table. Intersect. This problem faces 2 decision variables and 3 constraints. Now let's see why this problem is exceptional. Okay, this table contains 3 constraints. First, 5x1 plus 2x2 equal 1000. x1 x2 intercept when x1 equals 0, then x2 equal 500, x2 intercept when x1 intercept when x2 equals 0, then x1 equal 200. Point of x1 x2 on line 0 500 and 200 0. Move to the next equation. 3x1 plus 2x2 equal 900 if x1 equals 0, then x2 equal 450. If x2 equal 0, then x1 equal 300. The points are 0 450, 30 300 0. The last constraint states that x1 plus 2x2 equal 500, x1 equal 0, x2 equal 250, x2 equal 0, x1 equal 500. Points 0, 250, 50, 0, 500, 0. And x equals 0, x1 axis, x2 equals 0, x2 axis. Let's plot each equation on the graph. Now let us plot the previous point on the graph. A equal on the vertical axis, A 0, 250, B is the intersection point. We need to solve two equations simultaneously, and C is 300, 0. These are given. Now we are going, B is the point of intersection of lines x1 plus 2x2 equal 500, 5x1 plus 2x2 equals 1000. On solving simultaneously two equations, the point of B is 125 and 187.5. So now, as we mentioned before, in the problem of maximization, usually we deals with the points of intersection closer to origin point, the closer one. In case of minimization, we deal with the points far from the origin points. Okay, now let's make the substitution of the given points in order to find the maximum profit in the next slide. Okay, referring to the graphical points. So now we have 3 points, corner points: A where x1 equals 0, x2 equal 250, B equal B where x1 equal 125, x2 equal 187.5, C equal 200 for x1 and 0 for x2. Let us substitute this value in the objective function. Z at the point of A equal 100 times 0 plus 40 times 250, which is equal 10,000. Z equal 100 times 125 plus 40 times 187.5 equal 20,000. The last, Z equal 100 times 200 plus 40 times 0, also the result is 20,000. Therefore, the maximum value of Z occurs at two vertices, B and C. gives the maximum value of z. Thus, there are multiple optimum solutions for the LPP. This is the first case, the first exceptional case in linear programming problem. The second exceptional case is unbounded solutions. Use the graphical method to solve the following linear programming problem. Given objective function max z equal 3x1 plus 2x2 subject to the following constraints: 5x1 plus x2 more or equal 10, x1 plus x2 more or equal 6, x1 plus 4x2 more or equal 12, and x1 x2 as more or equal 0 as non-negativity condition. Solution: to represent the constraint graphically, the inequalities are written as equalities. Every equation is represented by a straight line. To draw the lines, 2 points on each of the lines are found as indicated in the following table. Intercept. How we have three equations: 5x1 plus x2 equal 10, x1 plus x2 equal 6, x1 plus 4x2 equal 12, x1 equal 0 for the first equation, x1 equal 0, then x2 equal 10, x2 equal 0, then x1 equal 2. The point of x1 x2 on the line 0.10 to 0. The next equation is x1 plus x2 equals 6, x2 equals 6 when x1 equals 0, x1 equals 6 also when x2 equals 0. Point of x1 and x2 on the line 0, 6, 6, 0. The last is x1 plus 4x2 equal 12, x2 equals 3 when x1 equals 0, x1 equal 12 when x2 equals 0. The points of x1 and x2 are 0, 2, 12, 0, and x1 equals 0, x1 axis, x2 equals 0, x2 axis. Plot each equation on the graph. The visible region, as you see, is unbounded. This is the maximum value of z occurred at infinity. Hence, the problem has an unbounded solution. Check the visible region. The problem is of maximization. That's why this is a very exceptional case. Very exceptional case. The visible region is unbounded. Thus, the maximum value of z occurs at infinity. Hence, the problem has an unbounded solution. The case number 3 is no visible solution. Example: use graphical methods to solve the following LPP. Max z equal x1 plus x2, subject to x1 plus x2 less than 1, negative 3x1 plus x2 less than 3, and x1 comma x2 more or equal 0. Solution: to represent the constraint graphically, the inequalities are written as equalities or equation. Every equation is represented by a straight line. To draw the lines, 2 points on each of the lines are found as indicated in the following table. Intercept. So as you see on this table, two equations, x1 plus x2 equal 1, x2 equal 1 when x1 equals 0, x1 equal 1 when x2 equals 0, points of x1 and x2 on the line 0 1 1 0. Okay. Negative 3x1 plus x2 equals 3, x1 equals 0, x2 equals 3, x2 equals 0, x1 equal negative 1. Points are 0 3, negative 1 0, and x1 equals 0, x1 axis, x2 equals 0, x2 axis. Plot each equation on the graph. So by plotting the point on the graph, as you see, we found various visible solution, there being no points x1, x2 common to both the shaded region. We cannot find a visible region for this problem, so the problem cannot be solved. Hence, the problem has no solution. It is obviously there is two shaded region and no determined value of x1 and x2 clearly. That's why there is no visible solution. Exercise 1. A furniture manufacturer makes two types of products, chairs and tables. Processing of these products is done on two machines, A and B. A chair requires 2 hours on machine A and 6 hours on machine B. A table requires 5 hours on machine A and no time on machine B. There are 16 hours per day available on machine A and 30 hours on machine B. Profit gained by manufacturer from chair and table is $2 and $10 respectively. Solve this problem to find the daily production of each of the two products. Exercise 2. A company manufactures two products, Q and W, on 3 machines, A, B and C. Q requires 1 hour on machine A, 1 hour on machine B and C, and yields a revenue of $3. Product W requires 2 hours on machine A and 1 hour on machine B and C, and yields revenue of $5. In the coming period, the available time of 3 machines A, B and C are 2000, 1500 and 600 hours respectively. So try to find the optimal product mix which maximize profit. Exercise 3. A manufacturing company produces 2 models of TV sets, namely Model A and Model B. Model A fetches a profit of 20,000, whereas Model B fetches a profit of 10,000 per set. Both the models use the same time of picture tubes. Every month there is a supply of 400 pictures. Model A requires 8 hours labor and Model B requires 5 hours labor. Total labor available per month is 2,600 hours. Find the optimal production of Model A and B. Number 4. Use graphical methods to solve the following LPP. Maximize Z equal 7x1 plus 3x2 subject to the constraints x1 plus 2x2 more or equal 3, x1 plus x2 less or equal 4, zero less x1 less x5 over 1, or less equal x2 less equal 3 over 2, and x1 comma x2 more or equal 0. 5. Use graphical methods to solve the following LPP. Max Z equal x1 plus x2 over 2. Subject to the constraint 3x1 plus 2x2 less than or equal 12, 5x1 equal 10, x1 plus x2 more or equal 8, negative x1 plus x2 more or equal 4, and x1 comma x2 more or equal 0. The last exercise 6. A firm makes two types of furniture, chairs and table. The contribution to profit by each product as calculated by the accounting department is $2,000 per chair and $3,000 per table. Both products are to be processed on 3 machines, M1, M2 and M3. The time required in hours by each product and total time available in hours per week on each machine are as follows. How should the manufacturer schedule his production in order to maximize profit?